The chemical behavior of elements in groups 16 through 18 is a direct physical consequence of fundamental subatomic forces. Groups 16, 17, and 18 follow a consistent structural rule. The differentiating electron, the last one filling the atom, always enters the p orbital. The nucleus exerts a pull on valence electrons, but inner electron shells act as a physical shield, reducing the effective charge that reaches the outermost edge. This effective nuclear charge, or Z effective, equals the atomic number minus the shielding constant of the inner electrons. In heavier elements, inner d and f electrons provide exceptionally poor shielding. Their diffuse shapes allow more of the nuclear charge to reach the valence shell. This increased effective nuclear charge pulls the outer electrons closer, tightening the atomic radius. A higher effective nuclear charge also increases electronegativity and ionization enthalpy, as the nucleus holds the valence electrons with greater force.
Periodic trends result from the mathematical competition between nuclear charge and electron shielding. Period 2 elements, like oxygen and fluorine, are subject to strict orbital constraints. Because these elements lack d orbitals in their valence shell, they are limited to a maximum covalency of 4. In period 3, elements like sulfur and chlorine have access to empty d orbitals. These orbitals allow electrons to be promoted into an excited state, creating additional unpaired electrons for bonding. This octet expansion enables higher oxidation states, reaching +6 for group 16 and +7 for group 17. However, in the absolute heaviest elements like polonium and astatine, the inert pair effect becomes the dominant physical force. These atoms have such high nuclear charges that the s orbital electrons are held too tightly to participate in bonding, making lower oxidation states more stable. An element's reactive potential depends on its access to empty d orbitals and the stability of its valence s electrons. The F2 bond has a lower dissociation energy than the Cl2 bond. This weakness is caused by fluorine's exceptionally small atomic radius. The compactness of the molecule forces non-bonding lone pairs into close proximity. The resulting intense electronic repulsion between these tightly packed lone pairs heavily destabilizes the entire molecule, significantly weakening the chemical bond between the atoms. We see similar anomalies in the boiling points of period 2 hydrides, like water and hydrogen fluoride. The small size and high electronegativity of oxygen and fluorine lead to intense intermolecular hydrogen bonding. These hydrogen bonds lock molecules together, requiring high thermal energy to sever the connections and vaporize the liquid. The compactness of period 2 elements makes their own electron density a destabilizing factor in bonding. Molecular oxygen is paramagnetic despite having an even number of valence electrons. Molecular orbital theory allows us to map the true energy levels of the O2 molecule. Electrons fill the bonding orbitals sequentially and move toward the higher energy anti-bonding orbitals. The final 2 electrons occupy the degenerate pi*2px and pi*2py orbitals, remaining unpaired. Paramagnetism results from these unpaired electrons, as predicted by the molecule's orbital energy levels. VSEPR theory states that valence electrons around a central atom arrange themselves to minimize spatial repulsion. In chlorine trifluoride, the central chlorine atom has 3 bonding pairs and 2 lone pairs, creating a steric number of 5. Lone pairs occupy more physical space than bonding pairs. To minimize 90-degree repulsions, the lone pairs occupy equatorial positions in a trigonal bipyramidal arrangement. This leaves the chlorine and fluorine atoms in a T-shaped geometry. Charge distribution can also be delocalized, as seen in the resonance structures of ozone. We determine the most stable structure by calculating formal charge, which identifies the distribution of valence electrons across the molecule. Geometric symmetry can also cause individual bond polarities to cancel out, resulting in a nonpolar molecule. A molecule's shape and charge distribution represent nature's path to the lowest possible energy state. Moving down their groups, hydrides and hydrogen halides follow specific physical trends. As the central atomic radius increases, the orbital overlap with small hydrogen atoms decreases. This reduced overlap leads to lower bond dissociation enthalpies and decreased thermal stability. Weaker bonds allow for the easier release of hydrogen ions, causing acid strength to increase around the group. Oxides are classified as acidic, basic, or amphoteric based on the electronegativity and oxidation state of the central atom. Macroscopic properties like boiling points and acidity derive from atomic size and bond strength. Oxidizing and reducing agents are defined by the transfer of electrons and shifts in oxidation state. In a disproportionation reaction, a single element is simultaneously oxidized and reduced. When chlorine reacts with a basic solution, its neutral oxidation state of 0 splits into two different paths. Chlorine atoms are reduced to chloride at -1 and oxidized to chlorate at +5. Interhalogen compounds are generally more reactive than diatomic halogens because their mismatched bonds are easier to break during halogenation. Chemical reactivity and redox stability can be predicted by evaluating oxidation states and identifying weak bonds. Xenon, typically categorized as inert, reacts directly with fluorine. Because xenon is a large atom, its outer electrons are far from the nucleus, resulting in a low ionization enthalpy. Under the influence of electronegative fluorine, xenon's valence electrons unpair and promote into empty d orbitals. The resulting sp3d2 hybridization creates a square planar geometry, with lone pairs positioned axially to minimize repulsion. Every geometric shape and reaction in the p block is a predictable result of effective nuclear charge, orbital mechanics, and VSEPR theory.